Also, when it's. I'll be dead. All right. Okay. So remember last time you guys were here, we talked about vectors just in a very basic, superficial way. Like that they're arrows instead of points, and you can add them and you can find their lengths and all that stuff. And then we barely got into the calculus of them, talking about how they're like vector functions are good for like two-dimensional movement if you're moving that way and this way, or in some combination of that. Then you can bring it down into like horizontal movement and vertical movement and vector valued function, like combine the two so that you get some sort of interesting movement in two dimensions. And then we said to do calculus on vector functions, it's all like what you would hope, it's all what you expect. You just take the limit of for limits, derivatives, or integrals, you just do whatever you're asked for on each of the two functions on there. So the last thing we did was this limit. Now they're asking find the tangent vector to the function when t equals 3, which just in different words is just asking you for the derivative of that. And I'll explain what the tangent. Actually, maybe I should explain it now and then take the derivative rather than vice versa. So watch this tangent vector. Let me graph this on Desmos so you see kind of what this function looks like. And then I'll explain what the tangent vector means. Put this over here, put this over here. Graph it. Sine squared of pi over 2 times t, comma, t squared plus 7. And let me go from, I don't know, -10 to 10 or something. Okay, there's that function. When you see it, maybe it makes sense why it looks this way. On the x-axis, you're just doing a sine squared, so going from 1 to 0, 1 to 0, 1 to 0. And on the y, you're going up forever by more and more and more and more. So you get with those little short wavelength, getting bigger and bigger and bigger as y grows quicker. But what this is asking for is that when time is 3, so at this point right here, at whatever point comes out, this point right here, get the vector that is tangent to it, as in get the line that goes like this.
Get the tangent line on the function.
It's almost a tangent line, but it's easier than a tangent line because you don't have to get the equation. The vector itself will be everything you need, like the derivative itself. So you'll see what I'm talking about once we get the derivative. But that's intuitively this is what we're doing is we're getting the tangent line to that function or that equation, those parametric equations. Okay, so like I said, take the derivative of each of these, plug in 3, that'll be the tangent vector. So v prime of t would be, again, it's a vector. It's the derivative of this one, comma, the derivative of that one. And the derivative of the first one, I'm going to see if you guys get it right. So here's like 30 seconds, see if you can get that derivative.
Well, the next one.
A hint is don't say it's cosine squared. It ain't that. That's what everyone say it is. Nice. Nice. Yeah, really cool. Yeah. Okay. I don't know if that was enough time, but just for the sake of getting through a lot of content, let me tell you that you should have looked at this and seen two different chain rules. This is the function. I'm going to erase this in a second, so you don't have to write this. But this is the function sine of pi over 2 all squared. So you can see here's one function, here's the second function, and then here's the third function, the squared bit. So two different chain rules, you should have looked at it. And if you go from the outside in, you would get 2 times leave the inside alone. Times the derivative of the next inner function, which would be the sine function. So times cosine of leave the inside alone. Times the derivative of the very inside, which is just a linear function. So it should have had derivative pi over 2. This is the times. Boom. That's what you should have got. And you can make this probably look nicer if you said 2 pi times all this over 2. Maybe it looks a little nicer, but there you go.
Two's cancel.
Oh, that was cool. Yeah, look at this 2 could cancel this 2 if you wanted to. And then it's not that ugly of a function. But I'll deal with that later. And then, or like, I'll simplify it later. And then the derivative of the second one, hopefully, that one wasn't that crazy. That should have been just 2t. And then again, that'll give you the tangent vector at any point. Plug in a 3 and you will get the tangent vector when t is 3, obvious. So v prime of 3 would equal pi times, let me just do it little by little, 3 pi over 2 times cosine of 3 pi over 2, comma 6. And then, and then this is easy because cosine of 3 pi over 2 is 0. So you get something times 0 is all 0. So that's equal to 0, comma 6. Cool.
So what does that look like on the spec?
Yeah, that's what I was jumping to next. But if you're good with the numbers, let me show you graphically. Okay, watch this. That now on the graph would look like this. Give me a sec. I want to draw on it so that the video people see it too. So I think I put this. Can I draw on this? Yeah. Okay. So watch this. 0, comma 6. That was our tangent vector. That looks like this. Starting at the origin, going up 6. 1, 2, 3, 4, 5. So like that. And so very clearly that's the tangent vector to that. Just kidding. What's going on if you don't know about vectors? Wait, let me say this, Bree. Let's say that later. Listen to this. What's going on if you don't know about vectors that much is that it doesn't matter where you start your vector. All that matters is like how long is it and in which direction it's going. So I'm saying this is the tangent vector there because if you just take this boy and you move him up here, whoop, like that, then you can see that it actually is the tangent vector. So for the people on the video who didn't see me make this gesture, I'm going to take this guy, put it here, and you can see that you get, maybe I made it longer, but that's supposed to be 6 long, and that's the tangent vector. Cool. Now if you're going, yes, I see that that's tangent to it, but what's the 6 length have to do with it? Like, couldn't this be the tangent vector if I just made it like this much shorter. Yes, that's tangent, but what the 6 tells you is like, okay, the easiest way to explain this is if you interpret this like motion. Like if this is the path that the little particle is moving on, and then the interpretation of this is boop, 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 you're moving along this. If you were to keep moving in the same direction that you were moving at the same speed, that when you get to this point, this black point right here, then how far would you move in one period of time? And where would you move to in one? Like, let's say these are measured in seconds. If you're moving like this particle, and then you get to t=3, and you keep moving in the same direction for 1 second, where would you end up? That's what this vector tells you, is it's telling you you'd end up right there at the end of that vector. Okay. It's a lot, there's a lot to keep track of, but hopefully it all makes sense. The good news, or maybe I don't know if it's good news, but in terms of what you'll see, what you'll get asked for on the AP test, you don't have to necessarily understand all the intricacies, although it helps a lot more if you understand the concept, because then you know what you're doing. But if you're in a time crunch and you have to like skip out on studying this to the most like deepest degree, then you're okay, because on the AP test, they're just going to say, find the vector, the tangent vector to the thing, and you can just remember, okay, take the derivative. But of course, it's better to understand the concept. But okay, that's all for this one. Questions? Okay. Oh shoot, I gotta be done annotating others. This? Yeah, nice. Okay. Hang on, I'm looking on the video and it looks like my annotation is still there. So let me erase all the. And now go back to this. Okay. Next one is, okay, we did a limit, we did a derivative. Next one is an integral. Do the integral of that vector valued function. Again, all that means is take the x integral and the y integral separately, then put a comma between your answers. So off to the side, let me do some scratch work. I got to do that integral, and I got to do this integral for the y. And that will be my answer. The red one is very easy to do. Let's do it right now. Antiderivative of that would be 9t cubed over 3, or in other words, 3t cubed. I'll put the plus c for a second, but there's a fancy thing you can do with vector value function with the plus c. But I'll tell you about that later. But this purple integral, I'm going to stay quiet and see if you BC kids remember how to take that. Because it's been like very, very long time since you've thought about this type of integral, because you've been doing all AB type integral. But a hint is that it's a VC only like integration technique. Now, improper is like when you get infinite, like when you go to infinite. I'll let you think about it for a second, not say anything. If you really can't, I mean, there's a good chance you guys can't make any progress again, because it's been months since you've thought about this. But I'll give you a hint in like 30 seconds. Think of all the BC.
Integration by parts.
Nice.
I don't remember how to do it.
Integration by parts is the one where you choose U and dV. It's like undoing the product.
So
Yeah.
You can bump with the upright and you're done.
Again, I'm seeing if you can make any progress at all.
the
But I'll tell you in like, I don't know, 45 seconds. Nice.
like
Like even the x, you know, the x, the derivative is x.
That's also not
I
exactly.
know, but we want the integral.
Yeah, so then.
this is no
X,
flex.
T,
So.
X, the integral. T, so it's
I mean,
Oh, maybe. Flat. Maybe staying on Scooby, I didn't post it. I'll post it later. I'll have to go back into my archives. Sorry. All right. Whether you made progress or not, let me not spend too much time on this problem. Hopefully, at least the name of integration by parts rang a bell. Integration by parts is, okay, the reason I knew it was that is because I see a product of two functions, and integration by parts is undoing the product rule. So you see function times function, you got kind of two options. Is it U substitution or is it integration by parts? And in this case, if there's no inside function, then it can't be U substitution. So you know it's integration by, or yeah, integration by parts. And the way that works is, remember, you choose basically first derivative of the second, and then you go backwards from there. So, but the traditional way to do it is called something U. That would be your first, and then you figure out the U, and then you figure out your derivative of the second. That's what we call dv traditionally, and figure out what the second function was. Okay. And then I don't know if you remember the guidelines, but in your heart, do you guys remember what you should choose for U in this case? Yeah, it's usually the polynomial one, the one that will have a simpler derivative when you take the du. Like when and that's why I'm saying it's usually the polynomial looking one, because then when I take the derivative of t, I just get 1 dt. So you get like a 1 degree simpler. Nice. And then once you choose your u, you kind of don't have a choice for dv. This is forced to be the rest of the integral. So e to the t dt. And then to find your v, obviously you take the antiderivative. So antiderivative of e to the t is e to the t. There you go. And then either you have to remember this formula or you can derive it yourself just using the product rule. But I showed you that way long ago. I don't want to spend the time doing that today. Eventually I can show you again. But you can also just remember the formula, which is, do you remember?
It's like something plus or minus the integral, and then you put the dv in it.
Yeah. So specifically it goes uv
Oh yeah.
minus integral of v du. Again, for the people watching at home, this is uv minus integral of v du. There you go. Again, you can come up with this yourself if you mess with the product rule, like the normal derivative product rule, put some integrals in there. You can come up with this yourself, but I'll show you 1v1 if you're interested. Okay, and then not done because I still have an integral to do, but at least that integral is now easy. You take the antiderivative of e to the t and you get another e to the t. And then I guess plus c at the end of this. Okay, and then now that was all scratch work. Now I can go answer this question. I can say that integral is equal to this antiderivative, comma, this red antiderivative. Tet minus e to the t, comma, 3dq. And then here's what I was saying is the fancy way to handle the plus c is, since you have an integral, or sorry, since you have a vector as a function, you can add a vector constant to the end of this. So in other words, this plus vector c is like the traditional way to handle that plus c. How is that the same as this blue comma this red? Is because if you think of that c as a vector, I guess just off to the side real quick, you'll have like I don't know what to show first, but according to our like side work. That's what our answer should have been. But what I did is I took this +1 plus C1 and plus C2 and made it its own vector off to the side. And so if you remember about adding vectors, what I wrote up there is the same as what I'm writing now. Because that's what I called vector C. So this is kind of a neat, fancy way to do it. Again, another time where you didn't understand all the intricacies of that. It's okay. Like, you could even just write it like this if you wanted to. But this is like what I'm pointing at right now with my mouse is like the traditional way to answer these questions. Okay. And then example 5, very important. I'm excited to get to it after this question. Sometimes I just saw like what we're doing today in normal class and AB class is one of the 2025 questions, and I read through what they gave points for, and they were very forgiving last year for things that they traditionally have not been forgiving for. Maybe they're getting more lenient, but you try not to forget the plus C. Usually they do. Oh, that's another, I don't know. If you just said plus C, unknown, like, because that looks like the same exact letter, but they might be forgiving. Again, I don't, that's up in the air, but I would guess, if I had to make a guess, I would say they would not. So a few points if you said C and C. Questions, Sawyer?
BC test. Are the AB topics the same exact as the AB test and then plus BC?
Yeah, the BC test is the AB test exactly. They just take some AB questions out and replace them with these. Exact same questions, yeah. Question.
I heard the AB part is easier for BC.
Sam says AB part is easier on the BC test than on the AB. And I
Like we get
I
the
don't
easier
have any-
questions out of the AB. Maybe just because people are smarter, they say it's easier.
yeah, maybe, I don't know. It'd be interesting to see, in fact, we could do this one day, remind me. But yeah, we could look at the 2017 AB test and the 2017 BC test and compare the ones that are different and see which ones are easier. But yeah, I don't know anything about what's easier, what's harder. All right, but speaking of AP test, AP test, this example 5 is straight from an AP test 2022 one, which was the year before I made this section of notes. And I keep saying it's important because it used to be absolutely 100% guaranteed that they put this question with different functions possibly, but usually it's like the same part A, same part B, same part C, same part D, every year on the test. I'm saying they used to do that because I told them exactly that last year, and then they changed it for the 2025 test. They put a polar function question on there, making me look bad. But it was like for 5 or 6 years in a row, it was this question. Then last year they changed it, but I don't know. I got to see what they do this year, if they're gonna go back to this or be ready for a polar function. But like I said, it used to be guaranteed on there. Now I'm not so sure, but it's still good to practice it in case they do go back to it this year. I'm saying in case, I don't know if you need the whole backstory, but I've seen like people's spreadsheets where they keep track of all this stuff, and what the AP test does a lot is like they do the same question, the same type of question 4 years in a row, then they do a polar one, then they go back 4 years in a row, then polar one, whatever. So good chance that this could be like this, but we don't know. But anyway, if you read through it, it's another particle motion one, except it's the fancy BC version where now it's 2-dimensional. So there's an X and a Y position rather than just a singular 1-dimension motion. But if you read through this, you're like, oh shoot, Mr. Cordero, this box that I'm pointing at for the people in the video. You're saying, oh shoot, Mr. Cordero, you put the AV version of this on here because this doesn't talk about any vector or anything. But that's why I'm saying this is good news, is because all of these concepts you already know. Now you just have to like generalize them to BC topics. So what you know and love is still true. Position, when you take the derivative, goes to velocity. When you take the derivative of that, it goes to acceleration. You already know that. Then speed is the absolute value of velocity. You already know that too. Except, tune in for this, that the absolute value of velocity is, now we're thinking of it as a vector. Do you guys remember what this notation means, absolute values of a vector? What we agreed that means earlier in the section? Keep going, I'll just scroll back up and show you. Anybody? Okay, what?
Blank.
Yeah, exactly. Good job. Then that's the magnitude. So you're still thinking of it as absolute value of it, but then you got to remember, oh shoot, this is a vector, so absolute value means length. So it'll really look like kind of ugly, but it'll be like the x function squared plus the y function squared. And again, you're talking about velocity. So it's x prime and y prime, the derivatives, the velocity functions, squared and squared. Okay, good with that. I say this every year, and then people tend to forget, and then they take slopes, and then they do weird stuff. But if you just keep this straight in your head, then it shouldn't be super hard. All right, displacement, again, is just like what you know and love. Displacement has always been the integral of the velocity. Same thing here, except now you'll do an integral on two functions instead of one, just like up there, what I'm pointing at here with my mouse. And then distance, again, you already know that that's the integral of the absolute value of velocity, but now you're thinking of velocity as a vector, meaning absolute value is length, like you told me before. So this will end up looking like integral from A to B of that ugly square root. Okay. Okay. Now let's actually do the problem. 7 minutes to do it. Well, a little bit more. Okay, we'll see how far we get. Hopefully we get all the way through. But it says a particle is moving along the plane so that its position x of t, y of t at time is greater than z, so any positive time. Then it says the particle moves in such a way that the derivative of x is this and the derivative of y is that. And then that time forward, it's at 1.5. Then it says find the slope of the line tangent to the path of the particle at time t equals 4. Notice there's a difference, but it's asking you for the slope of the graph that this makes. The shape of that graph. So you're just thinking of that graph as its own graph and like getting the slope of the tangent line. So without me reminding you, do you guys remember how to freaking take the slope of a thing, of a parametric equation? I'd have to think back all the way to like 2 days ago. No, not 2 days ago, like 3 days ago, Monday. You remember?
dy t over dx.
Yeah, remember slope is slope, like you knew in algebra 1, it's change in y over change in x. If you keep all these like conceptually straight in your mind, then you don't feel like you have to memorize a bunch of things. You already know a lot that slope is change in y over change in x. So slope equals dy dt over dx dt. And actually, this problem is only checking if you remember that, because they told you dy dt and dx dt. There's really not that much to do here. You just do let me do it in a separate line so I don't get in trouble with the equal signs, which they sometimes hate. That means that here's my slope, natural log of 2 plus t squared over square root of 1 plus t squared. And then that means that the slope at t equals 4 is just plugging a 4 to the. I'm gonna write it very formally with like an evaluation line, but you could just say slope at t equals 4 is, and then whatever number we're about to get. All right, there you go. There's me plugging in a 4. Oh yeah. It's opening day. All right, there's the slope. Then it asks you find the speed of the particle at t equals 4 and find the acceleration vector of the particle at t equals 4. So 2-part question here. Let me do it in red so you can see the different particle. All right, part B, find the speed of the particle. Again, it's just kind of checking if you remember the formula. There's not that much for you to do. The speed of the particle, as we just agreed up there, is the length of the velocity vector. In other words, the length of this vector at time 4. So the square root of 1 plus 4 squared plus the y part squared. Okay. And again, you guys know you could leave it here, or you can make it look a little bit nicer and say that's going to be 17 plus the natural log of 18 all squared, like that. Okay. Again, these are one more little trick is that they kind of help you out because you know that speed should be a number. So it should make sense that we got a number out of this. But I'm saying they help you out because then they also ask you what's the acceleration, but they remind you acceleration should be a vector. So acceleration vector should be like something, a vector. So for the acceleration vector, it is what you'd expect. I don't even gotta teach you anything. What am I about to do to get the acceleration vector?
Take the derivative of the derivative.
Take the derivative of each of these, put a comma between them, that's it. Well, and plug it. Yes, because they say it time 4. Okay. So take those derivatives and plug that in. Oh, if we had more time, I'd let you do it. But here's us all doing it together. A of t equals, all right, the derivative of the x part would be, for the square root part by itself, it would be 1 over 2 square root of leave the inside alone. But then don't forget the chain rule, so times 2t, which I'm going to put up here, 2t. You good with that, or was that too much step skipping? Okay. All right. You could have also written this, you guys know, as like 1 plus t squared to the negative 1/2 times 1/2. But I just think what I wrote looks nicer. And then comma, the derivative of natural log is 1 over leave the inside alone times 2t again. So let me just put that 2t up here. Okay. Are you good with that part? It was chain rules, 2 chain rules. You just have to know the derivative of natural log and the derivative of t squared and the derivative of square root. All right, cool. There's a of t, and then a of 4 would obviously mean plug a 4 into there. So that would be, let me do it all at once. 2 times 4 is 8 over 2 times square root of 17. And this would be 8 over 18. Oh, also, I forgot to say this, but also this is always or almost always on the calculator section of the test. So if you wanted to be lazy and make Desmos take this derivative and that derivative when t is 4, you could. You could just say x prime of 4, y prime of 4, and write that answer down. But they would want to see probably what you typed into your calculator, but more on that later. 41. Let's be done there. I don't want to rush it. I think we could get it done in 4 minutes, but I want you to understand everything and not have to rush it. So let's be done there. We'll take 3 days on this, but tomorrow's Friday and we do have class. Tomorrow we'll try to like finish this and start the next section because I don't want to get behind. All right. Good work, y'all.
Nope.